Hello and welcome to another walkthrough video of IAL Edexcel AS Level Physics Paper 2, Unit 2, WPH12/01, October 2024. Section 1 we have already done in the previous video, in which we have done the MCQs from 1 to 10. Today we will do the subjective part, which has questions from 11 to 19. And before going into details, please subscribe and like my channel. I really need your support because I put a lot of effort in making videos for you. I try to help you guys out there, and in return, I really need your support. I really need watch hours on my channel so that I can excel further. Okay, so it is my kind request to you, please subscribe my channel and share it with your friends and family members as well. And if any one of you need any help in physics, you can reach me on the numbers and my contact details shown on the left side of this video. Question number 11. A beam of electrons passes through a thin layer of graphite. Okay, the electrons are then incident on a fluorescent screen, causing a series of rings to form as shown. Explain what the rings show about the nature of electrons. Okay, so if you see that the electrons ray is coming, passing through the thin layer of graphite and then expanding and making the circles here. What is that? This is diffraction. And diffraction is the property of wave or particles. If a ball is coming out from here and it is passing through the thin layer, will it become so many balls out there like this? No, it will never. It will remain just one ball, because diffraction means expansion of light from single part to many other parts, right? Spreading of light when it passes through the narrow cavities. Okay, this is called diffraction. So diffraction is a property of waves, not particles. So here, when electron passes through the graphite and then produces rings, it means it is expanding. I mean, the energy is expanding in terms of rings. We are seeing the light. So that shows the wave nature of electron. Electron is actually having both natures, particle nature and wave nature. Which phenomena in physics describes the particle nature? Photoelectric effect. Which phenomena describes the wave nature? The passing of electron through the grid, and then we see the rings on the screen. This is actually happens because of the diffraction. So what you are going to write as an answer to this question, you will write that the rings are formed on the screen because of diffraction. Okay, or either you can say this is point number 2, this is point number 1. The rings show a diffraction or wave nature of electron. Okay. Question number 12. Copper wires are used to connect a length of nichrome wire to a cell as shown. The copper wires and the nichrome wires have the same diameter. Copper has greater number of conduction electrons per meter cubed than nichrome. Explain how the average velocity of electrons in the copper wire compares with the average velocity of electrons in the nichrome. Okay, so for this question, you need to know the formula for an drift velocity, or average number of electrons that are flowing through the wire, N, A, Q, and V. This is called drift velocity. And from where do you get this formula, by the way? You get this formula from the basic concept or basic formula of current, which is Q over T, right? And when you have Q, just one charge, you can have so many charges, not just one. So we can write small q as charge per unit volume, because this is called charge density. Okay, this is total charge, by the way, and I'm just interested in to find the charge per unit volume. Okay, what I'm doing, I'm telling you from where do we get this formula. So I'm going to put in q over v, t, where v is volume. Okay, now I can, because I know that the volume is actually equals to length into width into height, you can say, or pi r square h for the cylindrical shape of the wire. So pi r square means area, and then h means the height or the length, maybe you can say. So we can write AD over T or AQ over T, right? Something like that. Okay, so now we are going to have from here. Okay, my apologies. From small q equals q over v, so this should be like that, because capital Q will be equals to capital Q will be equals to small q times v. Okay, so now we have this much here. Volume equals AL, so we are going to write, okay, we can take it here, I equals QV over T, okay, and then we have the volume to be equals to AL over T. Okay? Then we also know that distance over time, or length over time, should be equals to how much? Speed. Okay, so this is actually that speed that we are talking about. Okay, and this is true for one electron or one charged particle. But if you have so many charged particles, then you have to write N, A, Q, V, okay, where N is number of electrons per unit volume. Okay, per unit volume. So this is what they're giving you here. Greater number of electrons per unit of volume, or per cubic meter. Per cubic meter, meter cube means volume. Okay, so I hope you understand that the formula. How do we get this formula? NAQV. Okay, now come back to the question. They are saying from here you need to know that I equals NAQV, where this N is equals to number of electrons per unit volume or per meter cubed. Okay, and for copper we have the same current because same battery for both. We have same area because diameter is same, and then we only have two things to compare: the speed and the number of electrons per unit volume. Okay, so all these things are constant, so we are only left with N equals I equals I over AQV. Okay, so this refers to this. Actually, from this point, our answer starts for this question. Previous all the explanation that I have given you previously was just a background for your understanding, for your clarity of the concepts. So N is inversely to 1 over V. All right. Now you see that they're telling you that copper has greater number of conduction electrons per cubic meter. It means N of copper is greater than N of nichrome, right? So they're asking you for which of the metal they will have average speed higher or lower, or why. Okay, just compare the speeds. So when N for copper is higher as compared with nichrome, then of course speed for copper will be lower because they are an inverse relationship, right? And speed will be nichrome. So what you are going to write? You will write first of all NAQV, then you will write N is inversely to V, then you will write since N of copper, which is number of electrons per cubic meter length, greater than N nicron. Therefore, the third point, therefore, the speed in copper will be less because speed and number of electrons per unit volume are inversely proportional to each other. Okay. So this is the answer to question number 12. Question number 13. A hologram is an interface pattern that can be produced a three-dimensional image. To form a hologram, a beam of light from the laser is split by a beam splitter. The light then takes two different paths to photographic film as shown. Light is a transverse wave. Explain what is meant by transverse wave. A transverse wave is a light when a wave, or you can say in transverse wave, particles of the medium move or vibrate perpendicular to the direction of propagation of wave. Okay, so if light is going like this, I mean wave is going this way, but the particle will be moving up and down. So this is like perpendicular up and down motion of the, if this is rope is a medium, right? And the wave is moving in the rightward direction, so the rope will be moving up and down. It means the particles of the medium, like I mean rope, is moving perpendicular to the direction of propagation of wave. Propagation means the right side propagation. Light arrives the photographic film from two paths. Explain how this could cause constructive interference. Okay, first of all, you see here at number 1, partial light is moving this way and partial light is moving that way. So this light is reaching here first, but this way this light is reflected here, and maybe here. Okay, this from this mirror it is coming this way and then moving that way and this way. Okay, 5. Not 5, I need to number again for your understanding. Okay, partially light is moving this way and partially reflected that way. Okay, so 2. Now the wave is reflected this way and coming here. Okay, at this point here we are seeing the image. Okay, because this is the photographic film image of the object. So light is coming this way and the 3, and then we will say 4 and 5. Okay, 1 2 4 5 and 1 2 3. So you can see clearly that the light is taking 1 2 3, the path is longer, while 1 2 4 and 5 is shorter. So this is for sure that there will be a length difference between the two paths, and this length difference between the two paths is called path difference. And when we have the path difference between the two waves, which are monochromatic means monochromatic means they are being produced from the same source. We had initially single wave, then it is split into two waves. Okay, so it means both waves are being produced from single wave, so therefore the produced two waves will have same frequency. And when these two waves will, I mean, reach to this point number 6, they will meet each other. And when they will meet each other, either they will do constructive interference or destructive interference. Okay, now the question they're asking is, explain the question 3 that they're asking, explain how this could cause constructive interference. Okay, so I've told you the all explanation how it will happen. Now we will follow the explanation. Point number 1, light arriving. Okay, light, first of all, light is splitted into two waves at beam splitter. Okay, the two splitted waves will have same frequency and will meet at photographic film, and interference will take place between the two waves. Interference will take place. Okay, now the third and most important, if path difference between the two waves, path difference means one is covering more distance, one is covering less distance. So for example, if one is covering 3 and the other one is covering 6 centimeter, it means there is the path difference is actually equals to 6 minus 3. 3. So this 3 is actually integral multiple of the path difference between the two. Okay, 3 times 1, 3. 3 times 2, 3. It means the path, the difference of the path between the two total paths of the waves is actually integral multiple. And when it is integral multiple, we always have constructive interference. Okay, so now we'll see if the path difference between two waves is integral multiple of wavelength, which is written as n lambda, where n is 0, 1, 2, 3. We will say that constructive interference will take place, because this is the condition for constructive interference. Always remember that if they ask you what is the condition of interference, you will just say path difference between two waves should be integral multiple of wavelength. And if they say what is the condition for destructive interference, you should say that the path difference between the two waves should be half integral multiple of wavelength. Okay, so this is the answer to this question. Now if this path difference integral multiple of wavelength, we will have a constructive interference. Okay, 14. A student investigated the electrical properties of the light emitting diode. He varied the potential difference across LED. You see, they're saying varied. He varied the potential difference across LED. It means you have some mechanism in your circuit to change the potential difference. Okay, and recorded corresponding values of the current in the LED. It means you are measuring the current, so you must have ammeter in your circuit. Also, you're changing potential difference, so you must have voltmeter in your circuit. You should have LED in your circuit. Okay, the graph shows these results, and they're saying draw a circuit diagram the student could use for this investigation. So first of all, you should have a power supply. Okay, and for that you can make this circle as power supply, or you can use a battery sign as well, but you need to mention this is power supply. Okay, so better to use the symbol this power supply, or maybe this is fine. Okay, now you need to remember that they are saying they are varying the potential difference across LED. So first of all, you must have a variable resistor here to change. When you change the resistance of this variable resistor, the voltage across the LED will be changed. Okay, so this is your LED sign. Okay, and this is the light emitted from here, and you need to measure the voltage across LED. So for that you will connect voltmeter here. Then you have to measure the current in your circuit as well. So you will write you will apply the ammeter here, and then you will finally connect it to the negative terminal of the battery. Okay, so this is your complete circuit which is required to measure the voltage and the corresponding current in the circuit. Because you're changing the resistance, it means you're changing the voltage, and when you're changing the voltage, it means you're changing the current. So all these values will be displayed on the voltmeter as you are changing it here. Determine the power of the LED when the potential difference across LED was 2.2. It's pretty straightforward. 2.2. Okay, so this is 2.1, this is 2.2. Okay, this is 2.2, and this is here. So for me, it is somewhere at 32, 34, 36, and 37, and this is 2.2. So they're asking you calculate the power dissipation, and power dissipation should be V into I, and when V is 2.2, okay, then current was 37 into 10 raised to the power minus 3. Therefore, the power dissipation will be 0.018 watt. The student increased the potential difference across LED from 0 to 2.4. Describe without further calculations how the resistance of LED changed. So what will happen? Now here we will see that from the graph, we see that it is a typical diode. You see? The diode graph always starts from here like this. It always stays at 0 in this region because of forbidden gap. Okay, so let me explain you the concept of forbidden gap, because there is a band theory, like energy band theory. We have a theory in physics which we call energy band theory. Okay, according to this, you have three categories of materials. One is conductor, one is semiconductor, and one is insulator. Okay, now in semiconductor, they say, this theory says that in all the materials we have two kind of bands. One is energy valence band and one is conduction band. So this is conduction band and this is valence band, and you see that the valence band and the conduction band are overlapped in conductors. In conductors, the CB and AB, VB, sorry, I mean valence band are overlapped. Now, all the electrons are residing in valence band. This theory says all the materials have conduction band and valence band. And second point of this theory is all the electrons reside in the valence band and do not conduct electricity. Remember, in order, point number 3 for this theory, if a material wants to conduct electricity, the electrons should jump from valence band to conduction band, because that band will conduct the electricity. Okay, so in the case of metals, these bands are overlapped, so it is very easy for the electron to move into here because there is no gap, they're overlapped. So you can say that all the free electrons that are residing in the valence band are available for the conduction band to conduct. So it is very easy for the electricity to pass in the case of conductors. But this is not true for semiconductors, because now will be a gap. There will be a gap. Now you will see that the conduction band and valence band are separated by some distance, and this distance is called forbidden gap. Okay, so for example, electron needs 2 joules of energy to jump from here to here, because an electron must have energy to jump, right? If electron is hungry, he's not having enough energy to jump, he will never be able to jump, so he must gain some energy in order to jump, right? So this 2 joule is the energy that you are providing it through the external battery. And if your external battery is providing the electron with 2 joules or more than 2 joules, it will start moving into the conduction band, and as soon as they arrive in the conduction band, you will see the current started to flow. So your graph will spike up. Okay, before that there was no current because conduction band was empty, because no electron was moving from valence band to the conduction band, and the theory says, energy band theory says, the electron must be in the conduction band to conduct the electricity. Okay, since the supplied energy was not enough for the electrons to jump from the valence band to the conduction band, therefore there was no flow of the electricity. Therefore, we see no current in this gap, and this gap refers to forbidden gap. And this forbidden gap is always happen in the case of diodes, and diodes are what? Semiconductors. LED diode is what? Semiconductor. Therefore, in the case of semiconductors, you will always see such kind of graphs. Okay, and in the case of insulators, this gap is way too much of the gap between conduction band and valence band. No matter how much energy you provide to the valence band electrons, they will never reach conduction band. Therefore, in insulators, we say that there is no passing of the electricity. Okay, so that was the energy band theory which was required as the background to understand this question. I hope you understand this question now. Now they are saying describe without further calculations how the resistance of the LED changes as you move the voltage from 0.0 volts to the 2.4 volts. So we will see that, we will write that from here, from the graph. If you see the graph, we are we are we are we are unable to flow the current before 1.6 volts. Okay, so up till 1.6 volts there was a massive resistance, no flow of the electrons, because no electrons was available in the conduction band because of that forbidden gap, and that forbidden gap is actually resistance. You can see from the graph, we see that, point number 1, there is no current flowing from 0 to 1.6 volts. So we say that resistance is very high. In other words, we will say that no electrons are available in the conduction band to conduct the electricity. Okay, or from 0 to 1.6, no electrons are available in conduction band to conduct electricity. This means that the resistance is high, 0 to 1.6 volts, from 0 to 1.6 volts. And second point, as soon as we go from 1.6 to 2.4 volts, we see current spike, which means all the electrons have been jumped from valence band to the conduction, and therefore the conduction has been started massively. Okay, so it means the resistance has been now reduced. Okay, so we will say resistance reduces from 1.6 to 2.4 volts. Okay, okay. Question number 50. A strain gauge is an electrical component that can be attached to an object to measure the mechanical strain. This strain gauge shown has 6 metal strips attached to a small piece of insulating material. The metal strips are joined together by connectors. The initial length of each metal strip is 18 mm. Okay. Each metal strip has a rectangular cross section of width 1.4 mm and thickness of 0.23. The, the resistance between the terminals is 0.16 ohms. The connectors and terminals have negligible resistance. Determine the resistivity of the metal used to make the strips. Now you see how many strips are there? 1, 2, 3, 4, 5, 6. And each strip is not 2D. Actually, it is more like a 3D strip like this. Okay, like this. So they are telling you the length, which is 18 mm. And then they're also telling you the width and the thickness. Okay, the width, which is 1.8 into 10 raised to the power minus 3 meter. This is the length, and width is 1.4 into 10 raised to the power minus 3 meter, and the thickness is actually 0.23 into 10 raised to the power minus 3 meter. So by multiplying length into width, or width into thickness, we will have the base area, right? So area of base will be width times thickness, so it will be 1.4 into 10 raised to the power minus 3 times 0.23 into 10 raised to the power minus 3. So the area is going to be 3.22 into 10 raised to the power minus 7 meter square. Okay, now you have the resistance as 0.16 ohms, and you have the length as 1.8 times 10 raised to the power minus 3. You got everything, R, L, and A. Now you need to find the resistivity, and resistivity is actually equals to rho L over A. Resistance is actually equals to rho L over A. From here, resistivity, which is rho, equals to RA over L. So I'm just going to put in the values, and the values are 0.16, and then area is 1.4 into 10 raised to the power minus 3. Oh yeah, we got the area already. And the area is 3.22 into 10 raised to the power minus 7. 3.22 into 10 raised to the power minus 7. And then length is 0.18. Okay. Now there's a trick in this question. You have 6 strips. Okay. So if you connect these 6 strips together like this in a straight line, 1, 2, 3, 4, 5, 6. Okay. So the length will be increased, but the area will remain the same because we need to have the cross-sectional area, right? The cross-sectional area is not going to change, but the length should be multiplied with 6, right? So what we are going to do, we have to multiply the length of one string with 6. So we are going to have 1.8 times 10 raised to the power minus 3 times 6. Okay, so when you multiply all these together, you are going to get the answer as 4.77 into 10 raised to the power minus 7 ohms meter. Okay, I hope you understand the concept of why did I multiply the length with 6, because we have 6 rods and all of these are connected in series with each other. B, the strain gauge is stretched and the length L of the metal strip increases. Okay, the metal strip change shape uniformly along their length. Explain why a graph of resistance of the strain gauge against L square would be a straight line. The temperature of the metal strip is constant. Assume that the volume of each metal strip is also constant. Okay, so simply we have to show that the graph between R resistance and L square is straight line. That means R and L square are directly proportional to each other. And when they are directly proportional to each other, we will get this kind of graph, okay, between resistance and L square. So we need to show this through mathematical relationship. So we will start from R equals rho L over A. Okay, and volume is actually equals to area times height, or pi r square h, because the wire is like this. Usually it is in the shape of cylinder, and for the cylinder we have the volume as pi r square h. Okay, so for the time being we will write pi r square as A into h, or we will write h as L. Okay, just for understanding, because we have here L. So now A will be equals to V over L, or you can write small l, because in the question we have small l. Okay, so now we will plug in the value for area here. So rho L over V over L. Now this L will go upstairs and it will become rho L square over V. Now this is constant, therefore we will say that R is now directly to L square. So this is actually enough to answer your question of 3 marks, but we will say that this shows that the gradient of the graph between R versus L square is constant, and when the gradient is constant, it means the graph is straight line. Okay. Question number 16. A student investigated the diffraction of light from a laser using a diffraction grating. The diffraction grating has 250 lines per mm. The diagram shows the arrangement used. Give one safety precaution the student should take during the experiment. Of course, you're playing with the laser, so you should not directly look into the. Do not directly look into the laser. So this can be your one safety precaution. State what measurements the student should make to determine the wavelength of the light from the laser. Okay, because you're playing with the diffraction grating, so you have to use the diffraction grating formula. And diffraction grating formula is n lambda. Yes, n lambda equals d sine theta. Okay. Now, what do you think you should have for this wavelength? You should have d sine theta over n. Now you should have angle, you should have d, and you should have n. Now for that, we will proceed back to this diagram, because when light will pass through the diffraction grating, of course, it will expand like this, okay, and it will have so many dark and bright fringes. So for example, this is first order fringe, first order bright, or this is central, bright or dark, whatever. First order. First order means n equals 1 here, n equals 0, okay. Now this is actually theta. So in order to find the wavelength, you should find the distance this and this, right, and this theta. And when you have all these things, you will be able to find the wavelength very much easily, okay. So now, how will we write the question? We will write find d, which is distance between diffraction grating, dg I'm writing in short, you will have to write it full, diffraction grating, and central maximum, okay. Central maximum, the central spot, the brightest spot, okay. The central maximum shows brightest, minimum means the dark, okay. Then you have to find vertical distance x between central maximum and first order maximum, because if central is brightest, the first order will be brightest as well, okay. So you need to remember, you need to measure the vertical distance, and when you have the vertical measurements, find theta using tan theta, and tan theta is actually perpendicular times base. So what will be the perpendicular in this case? This will be your perpendicular and this will be your base. So perpendicular is x and base is d, right? Any problem with that up till now? I think you're understanding it well. And now when you have measured theta from here, because you will have this distance, you will have this distance, you will have theta tan inverse x over d, okay. Finally you have point number 4, find d, which is small d, using d equals 1, okay. And since you are having the lines 250 lines per mm, so it means it will be 10 raised to the power minus 3 over 250. So that will be the value for d. Now you got d, now you got theta, and you got the order, first order, n equals 1 as well. N equals 1 for first order. So the point number 6 will be find lambda using n lambda equals d sine theta, and lambda equals d sine theta over n. Okay. Now they have given you exactly the same. The student observed the two first order maximum. The angle between the two first order maximum was 18 as shown. State that the wavelength of the light from the laser is about 600 nanometers, okay. So we are going to split first of all into this. We are going to split the angles as well. We will talk about this only. So now we have theta equals 9, so don't need to measure this and this distance because you already got the angle to be 9. And then you also have d as 10 raised to the power minus 3 over 250, because the lines which are mentioned are 250 lines per mm. Okay, so mm, whenever you have lines per mm, just remember you will put 10 raised to the power minus 3 on the top and divide by the number of lines whatever they are given. If 800 lines per mm, just write 10 raised to the power minus 3 over 800. And if the lines are number of lines per meter, so you will just write 1 over 250. Okay, no 10 raised to the power minus 3, remember that. So this is your D. And finally, the answer for this will be 4 into 10 raised to the power minus 6 meters. And for first order, we have n equals 1. So wavelength is going to be n lambda equals d sine theta, and lambda will be d sine theta over n. Lambda equals d is 4 into 10 raised to the power minus 6. And this is sine 9. And this is 1. So from here, lambda is equals to 626 nanometers, or about 600 nanometers. The refractive index of the water is 1.33. Calculate the speed of the light in water. Okay, pretty straightforward question. N equals C over V. This is speed in air. Oh, my pen is not working. Please wait. And this is speed in medium. Okay, and medium here is water. So refractive index for water is 1.33, and speed of light in air is 3 into 10 to the power 8. And from here, V is equals to, I need to calculate. And while calculating, I gotta get 2.26 into 10 to the power 8 meter per second. Okay. Oh, someone is telling me that I have skipped one question. Okay, I believe I skipped this one too. The student observed maximum beyond the first order. Okay, determine the greatest order of maximum that the student could observe. Okay, so they're saying you're not up till here, you're seeing something here, 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 so many orders, right? So n equals 2, n equals 3, and so on. They're asking you, tell us up to how much value of n you see the pattern, the diffraction pattern on the screen. Well, for that, again, it's not that difficult. You will write n lambda equals d sine theta. You know that the wavelength is oh, my pen, d sine d sine theta over n, right? So because now what should we do with this? Because now we need to find the maximum n. For maximum n, this right hand thing should be maximum, right? Because this will be giving us the value for n. So in order to get the maximum value for n, we need to put sine theta as sine 90, and sine 90 is 1. Okay, so we will just left with d equals n, d over lambda. Sorry, this lambda will go there and cancel. So sine theta will be sine 90, and sine 90 will be 1. So now d is 4 into 10 raised to the power minus 6, and wavelength is 626 into 10 raised to the power minus 9, which is nanometers. So you got about 6.67, or round it up to 6 orders. So up to 6 orders, you will be able to get the spectrum. Okay, the first part we have already done. The second part. Okay. Hold on. Okay. A person is swimming underwater in a lake. The person looks up towards the surface. 3 rays of light A, B, C are incident on the surface of the water as shown. Okay. Uh-oh. Please wait again. Okay. Each ray changes direction on the surface of the water as shown, not shown. Light from ray A and B reaches the person's eyes. Okay, most of the light from C does not reach the person's eyes. Okay. So they are asking you, explain the paths of ray A, B, C after each ray changing the direction at the surface of the water. Okay, light A is reaching the person. Okay, so first of all, this is the boundary. So this is the normal here. Okay, then this is the boundary, this is the normal here, and this is the boundary, this is the normal here. Okay, so we have drawn 3 normals, and since they are saying ray A and B is reaching the person's eye, so it means light is moving this way and light is moving this way. Okay, and from C, light is not approaching C, so it will be moving this way, right? So from here, what do you see? you are seeing that this is the normal for A normal, it is C normal, and it is B normal. Okay. So here the light is totally internally reflecting. Okay, TIR. Here the light is bending towards the normal because it is coming from air to the water. Water is dense, air is not dense. So the ray is bending towards, actually the path was like that, but it is bending towards the normal. It is moving towards the normal. Okay. So we will say that we have to explain the path actually for each of the ray A, B, C. Okay. Let's talk about A first. Okay. For A, we will say light enters from air, which is less dense, to water, which is more dense, bends towards normal, and then this is 1 1. So reach person's eyes. And why it is bending? Because incident angle is less than the critical angle. This must be remembered by you that there are three conditions. When incident light is less than the angle of the incident light is less than the critical angle, then it will just bend from when it comes from one medium to another medium. When the light enters from one medium to another medium, three things can happen. Okay, either it bends towards the normal, either it bends away from the normal, either it bends across the boundary, something like that. For example, here it is moving in out, but maybe it was moving like that across the boundary. Okay, so it is also possible. This is called this is the condition when you have the angle of incidence equals critical angle. Okay, so first condition is this, in which the light only changed its path. Second one is this one, when light moves across the boundary, and the third one is when incident angle is greater than critical angle. So in this case, the third one, total internal reflection, only here refraction, and in this case along the surface. Okay, or at 90 degree, or at 90 degree to the normal. It means if we have this second condition, so now normal for C here is this, so light was like moving like this because the angle is now 90 between the normal and the reflected ray. Okay, but now it's not possible. So for path A, we have explained what do we have. For B, again you see the light is reaching the personal in only one case, that light is not moving out from here, so it is coming back, therefore person can see. So in here in B part, you will see that TIR, total internal reflection, and this is happening because uh-oh, and this is happening because incident angle is greater than critical angle. Okay, and for C, you will say that light enters from dense to water, to light moves from more dense, which is water, to less dense medium, which is air. Therefore it bends away from the normal, therefore bends away from the normal. And second point is, again here incident angle should be less than the critical angle. Okay, less than the critical angle, or you can say that incident angle can be equals to critical angle. In that case, it will be traveling along like this. Okay, so you can make this path or this path both, because there is quite possible that it is moving along the surface. In that case, incident angle will be equals to critical angle, but in that case, in both cases, either this one or this one, either this one or this one, the light is not approaching the person. Okay, so you will write this and this both. Okay, so you will write this and this both for part C. 18. The photograph shows the Golden Gate Bridge in San Francisco, USA. The bridge has two main cables. Attached to these cables are smaller suspending cables which support the road. Wind causes each suspending cable to oscillate, so standing waves from on the suspending waves form on the suspending cable. Okay, explain how a student how a standing wave can form on a cable that is fixed at both ends. So we will say that when, so for example, this is one end, this is another end, one wave is going this way, other is like coming this way, so we have two waves between fixed ends. So we can say that here we have two fixed ends and we have rope here, and it will be moving like that. Okay, so we can have the standing waves like going on like this. So how do we define? We will say when two waves of same frequency and amplitude. This is keyword, okay? See, frequency and amplitude, you have to remember. Travel in the same medium, and in opposite direction. This is also keyword, in opposite direction. Then they do interfere and create standing or stationary waves. Why do we call them standing? Because these waves are not going anywhere. They're just oscillating, moving up and down between two fixed ends. Therefore, they can be considered as standstill. Okay. The diagram shows a standing wave on a cable that is fixed at both ends, x and y. Okay. At both ends. Okay. X and y are 2 points on the cable. Describe the motion of x and y on the cable. So x shows antinode, y shows node. So antinode means max displacement from node, and this shows minimum or zero displacement. Okay. And yeah, I think that's quite enough for this. Or you can write maximum oscillation, one more, maximum oscillation, and here zero oscillation, or amplitude of oscillation is zero. In a strong winds, the Golden Gate Bridge emits a humming sound. Humming sound means something like that. One of the suspending cables on the bridge has a mass of 2.1 into 10 raised to the power 3 kg and a length of 87 meters. Show that the mass per unit length mu of the cable is about 24 kilograms per meters. Very easy. Mass is 2.1 into 10 raised to the power 3. Length is 87 meter. And mass per unit length is mu, or mass per unit length. So it is 2.1 into 10 raised to the power 3 over 87 equals. The answer is 24.1, which is rounded to 24 kg per meter. The lowest frequency of humming sound produced by the bridge is 280 hertz. Okay. Total mass of the road on the bridge is 140 kg. 140 times 10 to the power 6 kg. The weight of the road is supported equally by 500 suspending cables. The range of lengths of the suspending cables is from 3.5 meter to 1.160 meters. Okay. The value mu for all suspending cables is 24 kilograms per meter. Deduce whether the lowest frequency standing waves on the suspending cables could be producing the hummingbird sound. Okay, humming sound. Very important question, and very much has to be understood well. Okay, so these are the two bridges. Here do you have the road, and here you have the strings or the wires. Okay, this is your road, and these are your cables. And how much are they? 500, and the length is from 3.5 to 160 meter. So say this is 160 meter, and this is say 3.5 meter. Okay, and the weight is about yeah, the weight is not given. Okay, we need to find out the weight as well. So the total mass here, this mass is actually 140 into 10 raised to the power 6 times 9.8. So when we will do 9.8, all the weight of the road, which is weight of the road, will be acting downwards like this. Okay, 140 times 10 raised to the power 6 times 9.8, and this weight which is acting downward will create tension in the strings in upward direction. Okay, so there will be so many tensions in the string, right? And now we will see how do we solve this question. It is a tricky question, so stay with me. First of all, you have mass equals mass per unit length. Sorry. First of all, you have mass per unit length as 24 kilo per meters. Okay. Then you have the speed of sound equals T over mu, right? And also you have speed of sound equals f lambda. When you say that the lowest frequency sound, what kind of standing waves are referred by the term lowest? Okay, when you say lowest, it means between one cable you only have one loop. Okay, So the length of cable is differentiated from 3.9 to 160 meters. Okay. So for example, I'm talking about 3.5 meter for now. So length equals 3.5 meter, and this length should have half of the wavelength. I mean, this wave is half, not full. Only this part, I'm considering this part. So we will say that the length 3.5 meter contains half of the wavelength, just like standing waves constant. I know you understand it well. So we will have 2L from lambda 2 into 3.5, and lambda equals 7 meters. Okay. Now we have 7 meter, and we have equation number 1 here. This is equation number 2 here. We will compare equation 1. Comparing 1 and 2, we will get f lambda equals t over mu. Okay. And then we will put the value for the lambda, and the lambda is either 2L. You may write 2FL. I'm just putting lambda equals 2L t over mu. Okay. And from here, f equals 1 over 2L equals t over mu. Now we don't know what is the tension here. What is tension and how do we find these tensions? Because there are 500 cables, and 500 cables will have a large tension, and that tension will be equal to this weight, because downward forces are equal to upward forces. Okay. So we will say now tension should be equals to, now tension we need to find. For that we will say upward forces equals downward forces. So we will say 500 cables, and their tension should be equals to the weight which is acting downward. Okay. So tension will be equals to, weight is 140 into 10 raised to the power 6 into 9.8, which mass times 9.8 the weight, and divided by 500. Okay. So from here we will get the tension to be equals to, okay, let me calculate, 2.74 into 10 raised to the power 6 newtons. Okay. Yeah. Okay. So I'm removing all of it and moving to the next. Finally, we have T as 2.74 into 10 raised to the power 6 Newton. And we got length, first of all, 3.5, and then we will talk about 1.6 as well. Okay. It is 35, 3.5, and 160, sorry, not 1.6, 160 meters. Okay. So now, for now, we are going to write the formula f equals 1 over 2L and T over mu. Now we need to find the frequencies for both lengths, 3.5 and 1.160. And then we will see what do we have the answer, whether it is 280 or not. So it is 1 over, first of all, we will write for 3.5. F equals 1 over 2 into 3.5. Tension is 2.74 into 10 raised to the power 6 divided by mu, which is 24. Okay. And answer for this is 48.3 hertz. Okay. And similarly, for L equals 160 meters, F equals 1 over 2L over T over mu, 2 into 160. T is 2.74 into 10 raised to the power 6 divided by 24. And answer is 1.06 hertz. Okay. So your range is now coming out to be range of frequencies. It is from 1.6 hertz to 48.3 hertz. 1.6 hertz from here and 48.6 hertz from here. So this range is well below the threshold of the humming sound 280. So our conclusion is we consider the lowest possible frequency, which is only one loop. This loop. Okay. If we have more than two loops like this, or three loops like this, we could have the answer, but they have said for the lowest energy find, and the conclusion is the lowest frequency standing waves will not produce humming sound. Okay. 19. This is the last question. A photomultiplier is a device that can detect very low intensity light. Okay. In a photomultiplier, a metal plate called a photocathode is connected to the negative terminal of a power supply. Electromagnetic radiation incident on a photocathode can cause the photoelectric effect. Describe the photoelectric effect. Okay. So when light comes and strikes the metal surface, this is metal surface. This is incident light or photon. incident photon or incident light. When this incident light strikes the electron of the metal wire or metal surface and kicked out from here, freed electron, then this process is called photoelectric effect. Okay, so we say that emission of electrons from the metal surface when the incident photon comes and strike the electron in the metal. Okay, the photomultiplier can only detect electromagnetic radiation that causes the photoelectric effect. Okay, explain why the photomultiplier cannot detect some frequencies of electromagnetic radiation. Okay, this is quite for sure. You see, they have said that the photomultiplier can only detect electromagnetic radiation that causes photoelectric effect. Okay, so you have to know the concept of threshold frequency. And before threshold frequency, you also know that the formula for frequency or energy of photon. The energy of photon is actually equals to E equals HF. And from here, you can see that frequency is directly proportional to energy. So it means minimum energy means minimum frequency, or threshold frequency means minimum energy or minimum threshold energy, right? So for example, I'm explaining it in an even simpler way. This is an electron and it is bound by a rope of 10 joule. It is bound. It is bound by a rope of energy having 10 joules. Now this electron, the photon is coming and trying to free the electron, okay? But it only has an energy of 5 joules. So do you think will it be able to free this electron out of it? No, because the incoming energy is not enough to break this rope, right? Now what about 15? Of course it will going to free the electron because the incoming for energy is massive than the strength of the rope which is inside and keeping the electron inside the metal surface. So it means the minimum energy required to break this rope is 10 joules, and this 10 joules is actually called threshold frequency or threshold energy. Okay, now if you keep on sending 5 joule photons to free this electron, will you be able to do photoelectric effect? The emission of electron from here will not be possible, so no photoelectric will take effect. Okay, so when no photoelectric effect will take place, it means photomultiplier tube will not detect any light, because photomultiplier tube actually detects electrons which are freed from the metal surface, and then it starts to detect the incoming light. But if the electrons are not coming out from here, the photomultiplier tube will say nothing is happening, no radiation is there. Okay, so we need to answer this question in terms of threshold energy. So we will write because the frequency of because, or not because, we can write if the frequency of incoming photons is less than certain threshold, not certain, specific threshold frequency, then electrons will not come out of metal surface, and therefore no photoelectric effect will take place. Therefore, PMT or photomultiplier tube will not detect any light. Okay? See, visible light has a range of wavelengths from 300 nanometers to 700 nanometers. The work function of the material used to make the photo cathode is 1.48 electron volt. Deduce whether the photomultiplier tube can detect all wavelengths of visible light or not. Okay. I'm looking for the okay. Deduce whether photomultiplier tube can detect all wavelengths of visible light or not. So for that, we need to see that which wavelength has which energy. and the minimum detectable energy is this one. Work function means the minimum energy required to break the electron from the metal and free it. Okay. Again, I will make a metal surface. There is one electron sitting here and it is fixed with 10 joule energy. This photon is coming and hitting it with energy of 10 joule. It means it freed the electron out successfully. So this 10 joule is not 10 joule. It is actually 1.48 EV here, right? Now, if we need to check the 380 nanometer wavelength light, does that light has this energy 1.4 EV or not? If the 380 nanometer wavelength light has this energy, it means we will say that the photoelectric effect will happen and it will be detected. Similarly, we have to check for 700 nanometer as well. And if the light has this much energy, it means it will be detected automatically. Okay. So for that, we will write the equation. Work function or phi equals work function 1.48 EV, and for EV we will write 1.48 into 10 raised to the power minus 19 joules. And when we convert it into joules, the answer is going to be 2.4 into 10 raised to the power minus 19 joules. Okay. Now this is the work function. I mean, the minimum energy should be available in 380 nanometer light and 700 nanometer light. Okay. Now for 380 nanometer light, we will check E equals hc over lambda, right? And then we just put in the values 6.63 into 10 raised to the power minus 34. If you don't know from where do we get this formula, E equals hf and V equals f lambda. So here the speed is c equals f lambda, and from f equals c over lambda. Oh my pen. C over lambda. Okay. So we are just putting the value here. Okay. Equals hc over lambda. Okay. And lambda is 380 into 10 raised to the power minus 19. So when we get the answer, it is 5.23 to 10 raised to the power minus 19 joules. And for 700 nanometer now, E will be 6.63 into 10 raised to the power minus 34 times 3 into 10 raised to the power 8 divided by 700 into 10 raised to the power minus 9. So answer is, let me calculate, 2.84 into 10 raised to the power minus 19 joules. Okay. Now you see that the energy range, since we will say since energy of wave lengths 380 nanometer to 700 nanometer fall in the range 2.84 into 10 raised to the power minus 19 to 5.23 into 10 raised to the power minus 19, which is greater than the work function or minimum energy required to do the photoelectric effect, 2.4 into 10 raised to the power minus 19 joules. Therefore, photoelectric effect will happen for all kind of, for, oh my pen is not working, for all wavelengths from 380 nanometer to 700 nanometer. Okay. D. In the photomultiplier tube, actually this is the working principle of photocathode. So actually what happens when when the light falls here. Okay, let me explain you the working principle of photomultiplier tube. First of all, light falls here and an electron is freed and falls here. When this electron falls here, it turns into two electrons. Okay. And these two electrons go there, and then these two electrons are converted into four electrons, 1 2 3 4. Okay. And these four are then detected here. So you see it started with one electron and in the end it ends at four electrons. So therefore it is called photomultiplier tube. It is multiplying the electrons. Okay. So in the photomultiplier, the photocathode and several other metal plates are in vacuum as shown. So this is the arrangement or construction of a photomultiplier tube. An electron is emitted from the photocathode. Okay. So this electron is coming from the photocathode and hitting here, and it's having speed of 1.35 into 10 to the power 6. there is a potential difference of 108 between the photocathode and the first metal plate. Okay, so here and here it is, there is a potential difference of 108 volts. Calculate the kinetic energy in joules of the electron at the instant it collides with the first plate. Okay, so initially when the electron was freed from the metal surface because of the electromagnetic induction, it had some kind of initial kinetic energy. Okay, I mean at this point it had Ke initial. Then it traveled from here to here because of this potential difference, and it gained more Ke. Okay, so initial Ke was half mv square, half 9.1 into 10 raised to the power minus 31, and V is 1.35 into 10 raised to the power 6 square. Okay, so when we multiply all of them, we got 8.29 into 10 raised to the power minus 19 joules. Okay, so this is the initial kinetic energy. Now, if you know the concept of the gravitational potential energy, remember when something falls down from this point to this point ground, we say it obtained gravitational potential energy, right? Why? Because here the gravity is maximum, here the gravity is not maximum, right? So because of the potential difference, I mean here the gravity is max, here it is not max, so it falls through the potential difference, it moved toward the higher side. So we say that the gravitational potential energy is equals to mgh. Now it is electronics. Okay, so we see that this point is having, for example, 100 volts, and this point is having 208 volts. So there is a potential difference of 108 volts. 208 minus 100 equals 108 volts. So when electron moves between these 2 points of different value or different potential, it means it will gain some energy, just like a falling ball is gaining some energy, right? So we say that again, in this case, we say change in Ke equals change in Pe, right? So here we will say that again. In the electronics, the concept is absolutely same, but here we have electric energy, not gravitational potential energy. So we will say gain in Ke, gain, gain in Ke. So for that, we will say change in kinetic energy is actually equals to change in electric potential energy. Okay, and electric potential energy is actually equals to V times E. Okay, you need to remember this. Voltage into current, and it will be available in your formula sheet. Okay, and kinetic energy is actually equals to same, and this will be your gain. So kinetic energy gain will be equals to voltage, which is 108, and E is charge 1.8 into 10 to the power minus 19, which is charge for electron. So Ke gained is equals to, it is actually equals to 108 times 1.6 into 10 to the power minus 19 equals 1.73 into 10 to the power minus 19 joules or minus 17 joules. Okay, now total Ke is equals to total Ke equals Ke initial plus Ke again. So adding them all, it will be 8.29 into 10 raised to the power minus 19 plus 1.73 into 10 raised to the power minus 17. And adding them together, it will give you 1.8 into 10 raised to the power minus 17 joules. Okay. E. The electric circuit shown includes 4 resistors A, B, C, D, which applies a potential difference between adjacent metal plates. Okay. Each resistor has a resistance of 85 kilo ohms. Okay. So each one is having 85,000, 85,000, 85,000, 85,000. Okay. Right. When the switch is open means disconnected. It will be like this. I mean, it is not connected. It is like it is currently in a closed condition. But when it is open, it will be like this. I mean, disconnected. Open means disconnected. So when it is open, the potential difference across power supply is 1960. So this is power supply, and when it is not in use, it is 1960 volt. Okay. When the switch is closed, it means closed like this. I mean, switch on. Closed means switch on. So when the circuit is closed, the voltage across resistor A is 108. So here, up till here, 108 volt. It means out of 1960 volts, the remaining voltage of 1960 minus 108, I mean 1852, is somewhere here, dropped somewhere here, okay? Because 1852 plus 108 is 1960, okay? So 1852 volts is dropped somewhere here and here because of internal resistance or whatever. Now they're saying calculate the internal resistance of the power supply, okay? So first of all, you know that EMF is equals to terminal voltage plus internal resistance, okay? So let me give you the idea for this as well. This is like, for example, uh, a cell, and here you have chemical energy inside, okay? So all this chemical energy is creating 1960 volt for you. But when it reaches the terminals, positive and negative, maybe it drops up to 1700 volts, okay? So this concept 1960 is actually called EMF, okay? You will write 1960 equals, the terminal voltage is 1700, and where 260 gone, it lost in heat, resistance, friction, anything, because of the chemical changes of the reaction, you know, some energy is lost. So that is 260 volts. So that internal resistance actually is something that is lost inside the battery, okay? Therefore we say internal resistance, okay? Now this EMF should be equals to terminal potential difference and this much, okay? So from here we have the answer, because we need to find the internal resistance. So we will write EMF as E minus V over, not over, I into small r, because internal resistance always written is as small r. The other component, these outside the battery or power supply, are with capital R, but internal resistance with small r, just to differentiate between internal resistance and external resistance. Okay, so E minus V over I equals R. This is the formula that you need to answer or use for this question. Now, total, what is the total resistance of your circuit? First of all, total resistance, because all of these are connected in series connection. Okay, all resistors are connected in series, so we write series connection, and for that total resistance RT equals 85,000 times 1, 2, 3, 4. So 85,000 plus 85,000 plus 85,000 plus 85,000. Okay. So RT is equal to 3.40 into 10 raised to the power 5 ohms. This is your total resistance. And what is total EMF? 1960. So in series, we know that the current remains same, right? So current in circuit. How do we calculate this? This is our A point. This is our B point. I equals EMF over total. Okay, so E is 1960 and RT is 3.4 into 10 raised to the power 5. Okay, so from here the value for the current is actually I believe we should probably do it for the first VA, right? Yeah, I think it is better to do it for the first, not use EMF, because in EMF we will have the internal resistance. So why not we use this information to find out the current, which is same all across the resistors. So current in circuit using A resistance. Okay, so current will be equals to potential difference across A and resistance R. So R is 108 divided by 85,000. Okay, this will give you the current equals 1.27 times 10 raised to the power minus 3 amperes. Now you got total resistance and you got the current as well. So what should be the potential difference across other components? Okay. R total and I 1.27 into 10 raised to the power minus 3 amps. Now V equals I R total, right? And we have to, not total, this will give us the terminal voltage, right? The terminal. And for terminal, we have to consider all these circuits for terminal voltage. Because in the formula, we have EMF, then we have terminal voltage, and then we have this. So we need each and everything. E equals I equals 1.27 into 10 raised to the power minus 3. And total resistance is 3.4 into 10 raised to the power 5. So it is equals 432 volts. So out of 1960, which was inside at terminals, positive and negative, how much you're getting? 432 volts only. Okay. It means massive amount is being lost in the internal resistance of the power supply. And that is actually required condition for PMT, because PMT works at very low currents. So in order to keep the currents at very low, you have to keep the resistance very high. Therefore, internal resistance is very high in the case of power supply. It is not cell, remember. In cell, we have very small internal resistance, but this is power supply. So power supply has massive internal resistance, remember that. Okay. So terminal potential difference, we got 432. And finally, you have everything to calculate internal resistance. So E is 1960, VT is 432, plus I is 1.27 into 10 raised to the power minus 3 into R. And from here, 1960 minus 432 over 1.27 into 10 raised to the power minus 3 equals internal resistance. And calculating all of it, we get 1.2 into 10 raised to the power 6 ohms, okay, which is massive internal resistance. So here is the end of your AS level, IAL Edexcel AS level physics unit 2, which is WPH12/01, conducted in October 2024. That is the end of walkthrough of this paper. I hope you enjoyed it, and I hope you understood it well. If you like this work, please like and subscribe my channel. I really need your support. Please share my channel with your friends and family members. And I hope we will see a good time together. Wish you best of luck for your exam. And I will see you in the next video. Up till then, it's goodbye.